So this time we've been asked to find the bending moment diagram of this beam, which is the same simply supported beam with a 400 Newton point load that we've already calculated the shear force diagram for. And so the shear force, usually for a question, what you're going to be asked is you're going to be asked to draw the shear force diagram and the bending moment diagram for a single beam. What I've done here, I've just split up. We've done a heap of examples with shear force diagram first because it's quite easy, relatively speaking. It's relatively easy. But if you start trying to do shear force diagram and bending moment diagram at the same time right from the start, it gets super confusing. So I'll kind of split them up. And so what we're doing now is we're coming back to these questions and imagining we're doing the next part, which would be to draw the bending moment diagram. Now it can be useful to do the shear force diagram first because the shear force diagram will help you draw the bending moment diagram if you want to avoid doing too much maths. And because this course is primarily for the construction management and BTEC students, we're trying to do as much as we can with as little maths as possible. And so that's what we're doing here. Now, I don't know if you've ever heard the phrase of using a sledgehammer to crack a walnut, but that's basically what the method of sections is when we're doing this types of problem. So shear force diagram, remember back in week 2 we were finding the internal forces at a given point. The shear force diagram is just finding the internal forces at a point for every point. And so if you want to find the internal forces, or if one way to find the shear force diagram that would take a lot of work is to calculate the shear force at every point along that beam. We're going to do a selection of points, so we're just going to do a few points, and then we'll start to see some patterns. And that'll give us some shortcuts for drawing the bending moment diagram without doing too much work. Excuse me. So the first thing we're going to have to do is we're going to have to draw our axes. And we're remembering that when we're doing moment, we are drawing positive down the way. For bending moment, we're going to draw positive down the way. And because I kind of have some other tricks up my sleeve that I haven't told you about, I already kind of know what the maximum moment of this is going to be. And so I can start doing this on. So that's going to be 100. So it's going positive downwards. So these are positive moments. 300, 400. This here is moments, and it's going to be in kilonewton meters. Or is it? It's going to be Newton meters because that's in newtons. So it's going to be in Newton meters. Okie dokie. So let's run through and find some points along this using the method of sections. And so what we'll do first is, so again, what we are doing here is you're taking the beam, you're cutting it to make those internal forces become external forces. And this is the one point when you're drawing these pseudo external forces, these pretend external forces on, this is the point where you're thinking about what positive is for the internal forces. So positive for the moment is like so. So that's positive. And for shear, I'm going to, yep, that's right. It's that way. Up, left, down, right. That's all good. And so what we're going to do, even though I'm not calculating the shear, I'm just going to draw it on anyway. The reason for that is so that we're on the right-hand side, so we're using this one, going down the way. And so that would be, it's the shear at, and we're at about 0.5 meters here. Oh, not about, we're at 0.5 meters here. And the reason I'm drawing that on is because it's important for the moment as well, the shear here, but it means that I can take moments about either of these points. I could take it about the 0.5 meters, this position here, or I could take the moment about this point. The sum of the moments is equal to 0 about A, or the sum of the moments is equal to 0 about here, and it'll still work. If I don't draw this on, it won't work. So it just stops you getting confused. But I'm going to take the moment about this point where I've split it. That's where I'm going to take the moment. And that means that I don't have to worry about this shear, actually. It doesn't really matter what it is. What it would be is 200 newtons. Got to balance that force. But I don't have to worry about it because I'm going to take the moments about this point. It's got no lever arm, no moment associated with it. So to find the moments, we're just going to say sum of the moments is equal to 0. That means, so we've got 200. This distance here is 0.5 meters. so times 0.5. I should really draw this on the top so you can see what's going on here. So just remember this was, so that's 2 meters and that's 2 meters, just as it is in the diagram here. So back to this. So sum of the moments is equal to 0. 200 times 0.5 is clockwise, so that's negative. And then the other one's, this moment here, m at 0.5 is anti-clockwise. So therefore, m 0.5 is equal to, it's going to come over, it's going to become positive, so it's equal to 100 kilonewton, don't be an idiot, 100 Newton meters, so we're in newtons this time. I haven't really put things along here yet, so at 0.5, 1, 1.5, 2, why am I doing all that? Who knows? 1, 2, 3, and it's 4 meters long, the whole beam. And so we found our first point. At 0.5 meters along, we've got a moment of 100. If we go 1 meter along, direction of these is going to be the same. That V at 1 meter is just the 200 newtons again. If you did want to take your moments about A, this is the moment at 1, but I'll take the moments about the 1 meter point. So again, sum of the moments is equal to 0. That means that 200 times 1, that's negative, plus m1 is equal to 0. So that means that the moment at 1 meter is equal to 200 Newton meters, 200 Newton meters. So at 1 meter, we're 200 Newton meters. Now, just before we get to this point, so just less than 2 meters, might be easy, you know what I mean probably, but let's just write it so it's actually really something. So 1.999 meters. Then we're going to put our pretend external forces on the same direction again, 1.999, and just do the same thing again. You don't really need to write it out. You can think of it, this has to counteract that, and so we can just say that m1 in that direction must be equal to, oh, sorry, it was m1.999, m1.999 in that direction must be equal to 200 times, that's why I did the 2 minus 1.9999 just before you get to that point, which is pretty much going to be 200 times 2, which is 400 Newton meters. And so this is going to get up to, at 2, I haven't done 1.5, it's going to get up to here. Now, what you can see here is what's happening is each time as we move along, we're just increasing the lever arm to this point. And so the moment is proportional to this distance. And so it's a straight line. Basically, between the points 0 is less than x is less than 2, we have got the situation where the moment is just equal to that 200 newtons times the distance you've gone, 200 times x. So that would give us all the points in between. So that's 0.5, 0.25 would just be 200 times 0.25, which would be 50. And you could fill in all these points in between 1.5, 200 times 1.5 would be 300. And what are you going to end up with? You're going to end up with a straight line. And so between two forces, or when the moment diagram is going to be a straight line. So remember, the shear diagram was flat between two forces, but the moment diagram is going to be a straight line between two forces. Now let's see what happens on the other side. That's what it does, but let's figure out why. So now we're going just past the 2 meters. I like the 2 plus symbols better. So it's a tiny, tiny amount past the 2 meters. So we'd have our, I'll draw my shear down here this time, it'd have to be going that way. The moment would have to be going that way to get a positive internal, and that's m2 plus a little bit. So that is equal to m must be equal to, well, let's just write the formula because the situation's changed a bit. The sum of the moments is 0. What have we got here? So we've got 200 times 2 meters. So do the moments about here. So we've got 200 times 2 meters, and it's negative. And then we've got basically this 400 is going through this point and the shear is going through this point. So this would be V2 plus. So it's also going through that point. So we can just ignore those. So then we've got plus M2 plus a little bit. It's going to be equal to 0. So M2 plus a little bit, 2 meters, a bit past 2 meters, is going to be still 400. Okay, so it's not jumping or anything like that, not like the shear force diagram did. So when you got to a force with a shear force diagram, you followed the force. Moment doesn't work like that because the lever arm, at this point, the lever arm to that new force is almost 0. And therefore it doesn't change very quickly. So it's 400 times nothing at all. So therefore the difference that this makes is nothing at all. But that's not the case once you go a bit further. So now we're at 3 meters. Same again, shear that way, moment that way. We have to shuffle across a little bit for now. Sum of the moments is equal to 0, and we're going to do it about this point here. So we're going to do it about the 3 meter point. So therefore we're going to get minus 200 times 3. Then we're going to get, that 400 is going to start doing something now, it's plus 400 times, so we're at 3 meters, the 400 was at 2 meters, so that distance, that lever arm there must be 1 meter, so times 1 meter, plus 400 times 1 meter, and then the next thing we've got, we're doing moments about here, so that's so moments about this point, so that shear force does nothing, so therefore we're going to get plus at 3 meters, it's going to be equal to 0. Therefore, M3 is equal to, so we're going to get 400 minus 600. It's going to give us minus 200. We're going to take it to the other side. It's going to end up being plus 200. Kilonewton meters. Remember, positive is downwards, so it's going to be here. Now we're going to go right to the end. So pretty much at B, you'd actually have to be just a little bit short of B, probably. So you're just a little bit short of B. We'll call this 4, a little bit less than that. So we've got, and I'll just take off the end, so we know we're just taking a section just before B. Same forces again, shear down, 3 from these things, remember, sagging positive, up, right, down, left, positive. Did I say up, right, down, left? I mean up, left, down, right. So then just do the same thing again. Sum of the moments is 0, so we're going to get minus 200 times 4 plus 400 times 2 plus M3 is equal to 0. So therefore M3, that's minus 800 plus 800, so M3 is equal to 0 kilonewton meters. So that's that point here. And we can just use a bit of a shortcut here. Between forces, if there's nothing happening, the moment is going to make a straight line. So we can join up those points. And there we've got our bending moment diagram for a single point load at the center of a beam. So you do the same thing. Usually you just put on the value of the point. So we just put on that's 400. Just checking I got there. See, civil engineers never work in newtons. Newton meters. Newton meters. Let's just put them all on. Newton meters. So all of these are Newton meters. So 400 Newton meters. And again, you would just shade it so it's easy to see where it is. Now, we could have done this a bit quicker. How could we do it a bit quicker? Well, there's a couple of things we can do. The first one is instead of taking heaps and heaps of sections, we just say we're between two forces, so it's going to be a straight line. So then we would just calculate what's the moment going to be at 2 meters. where the force is. We draw that on. Then maybe we check what the moment is at the end as well, and maybe at the start. But at these points, it's going to be 0 because these are pinned connections. So you're going to have 0 moment at the end. You'd only get a moment at the end if you had some kind of fixed connection at the end. So we know it's 0 at both ends because these are pinned connections. Pins can't take any moment, so there is no external moment on the end. Therefore, there is no internal moment at that point. And so we know it goes back to 0. So we could just have calculated, just take a section here only, and then calculated that point, and then you know that moment is a straight line between forces, so then you just join it up with straight line, like so, and you'd be done. There is another trick you can use though, and that's to use the shear force diagram. So what you can do with the shear force diagram is if you look at that 200 kilonewtons, and you work out the area up to a certain point, so the area of this up to that point is just going to be 200 times, say, 0.5, so that would be 100. That means that you have to go positive 100 for your moment diagram as well, remembering positive is downwards. And similarly, so for each of these, for each meter you go along, the area under that, so if you get to 1 meter, then you just figure out the area under your shear force diagram. You're going to have to move, let me just have a look at this, so you'd have 200 times 1, which would be 200, so to your bending moment diagram is going to have gone to positive 200. So at any point, you're just looking at the area under this, that'll give you your moment. Now let's just keep going with that. Say we got to 400 here, so that's just 200 times 2, 400. Then we keep going. So we've now got 400 plus another negative 200 times 0.5, say, and you can see you're starting to come back down again. And so if the shear force diagram goes negative, that just pulls this back down again, because you just be still adding up the areas. You add up all this area, then you add on the area up to the point you're at, but this is negative, so you would take it away. Let me just show you for this one. So for this point here, the total area up to that point under that shear force diagram is just going to be 200 times 2. That's that first bit, this bit here. Take away, now we're at 2.5 here, so 0.5. So take away 0.5 times 200 because it's negative. It's a negative shear at that point, which is going to be 400. Take away 100, which is equal to 300. And so therefore you can figure out what this point here is. And so the moment at any point is just equal to the area under the shear force diagram. Another way to think about that is just to think about, look, for every 1 meter I go along here, this is constant, for every 1 meter I go along, I have to go down by this area. And so for every half meter I go along, this is half a meter, for every half a meter I go along, I'm going to have to go down the area under this shear force diagram. And so that for half a meter along, I'm going to have to go down 200 times a half, 100. And you can just think of it like that. Might be more logical if you take it for 1 meter. If I go 1 meter along, 1 meter along this way, I have to go positive, this is positive, positive's downwards, I have to go positive 200, just equal to the value of the shear force diagram. On the other side, this is negative this time. For every meter I go along, I do negative 200. Negative is the opposite direction, positive is downwards, so go negative. And so for every 1 meter I go along, I need to go down by 200. And all of these is just a different way of saying the gradient of the bending moment diagram, if it's something you know about, is equal to the magnitude and direction of the shear force diagram. So this value here tells you the gradient of this bending moment diagram, bearing in mind positives downwards. So here you've got a gradient of 200 Newton meters per meter. And on this side, you've got negative 200 Newton meters per meter. Okay, I'll summarize that a little bit more at the end. Let's move on to the next example.